Welcome back in lecture series on topic chemical thermodynamics. In last video we have studied about bond enthalpy and also we have solved numerical problems based on bond enthalpy. And today in this lecture we will learn about Hess law of constant heat summation. So let us see what is the statement of Hess law of constant heat summation. So according to this law, overall enthalpy change for the reaction is equal to sum of enthalpy changes of individual steps in the reaction. That means if the reaction is carried out in one step or in many steps, the enthalpy change for that reaction is same. That means the enthalpy change of a reaction depends only on initial state and final state and not on the path by which the reaction occurs. Let me see here one example, general example. A is converted into B and during this the enthalpy change is delta H0 R. Now if the same change is carried out in stepwise manner, that is in first step A is converted into C, then enthalpy changes delta H0 1. Then C is converted into D in second step, then enthalpy changes delta H0 2. And in third step, D is converted into B, then enthalpy changes delta H0 3. So the same change is carried out in three steps. Then A is first converted into C, C is converted into D, D is converted into B, or A is converted into B. Then according to Hess law of constant heat summation, the overall enthalpy change, that is delta H0 R, is equal to sum of enthalpy changes in individual steps. So these are the three individual steps, and sum of enthalpies, that is delta H01 plus delta H02 plus delta H03, is equal to sum of all these individual enthalpy changes of individual step is equal to delta H0 R, that is overall enthalpy change during the conversion of A to B. So that is nothing but the statement of Hess law. So sum of the enthalpy changes for step 1, step 2 and step 3 is equal to enthalpy change for the overall reaction. Now let us see the another example, that is formation of ammonia. Now hydrogen, 3 moles of hydrogen gas reacts with 1 mole of nitrogen gas, gives you 2 moles of ammonia gas, and during this the enthalpy change is minus 92.2 kilojoules. Now if the change is carried out in two steps, that is twice H2 plus N2 gives you N2H4. During this enthalpy change is plus 95.4 kilojoules. And in second step, N2H4 gas reacts with hydrogen gas and gives you twice ammonia gas. During this the enthalpy change is minus 187.6 kilojoules. Now if you add both these equations, then what happens? N2H4 is cancelled and you will get what? 3H2 plus this one H2 molecule. That means gives you here 3H2 gas plus 1 mole of N2 gas gives you 2 moles of ammonia gas. Like this, if you add both these, then you will get the same, that is minus 92.2 kilojoules. So overall enthalpy change during the conversion is same whether the reaction is carried out in one step or in a two step. And the most important application of this, that is can be applied to this reaction also. See here, carbon in converted into carbon dioxide by two ways, by direct method or by this method. That is, first it is converted into carbon monoxide and then carbon monoxide is converted into carbon dioxide. Now when carbon is converted into carbon dioxide in a single step, the enthalpy change is minus 393.5 kilojoules. But if the same change is carried out in two steps, in first step carbon is converted into carbon monoxide, then delta H0 1 is equal to minus 110.5 kilojoules. And when carbon monoxide is converted into carbon dioxide, the enthalpy change is delta H02 is equal to minus 283.0 kilojoules. Now, if you add the enthalpies changes in individual steps, then it equal to how much? Minus 393.5 kilojoules. That means overall enthalpy change during the reaction is same whether the reaction is carried out in single step or in number of steps. That means overall enthalpy change of the reaction is same, and it is equal to sum of enthalpy changes in individual steps. That is minus 110.5 kilojoules plus minus 283.0 kilojoules. That is equal to the same, that is minus 393.5 kilojoules. So application of most important application of Hess law, that is it is used to calculate the enthalpy change for those reactions whose enthalpy change cannot be calculated experimentally by adding, subtracting or multiplying the thermochemical equation. One more example, that is Born-Haber cycle. In here enthalpy of solution, we have studied that the crystal lattice enthalpy cannot be calculated directly, and it is calculated for NaCl, that is for ionic crystal. It is calculated using the Born-Haber cycle. Now see here in this reaction, in this diagram, the sodium in a solid state when combines with half Cl2 in a gaseous state, it gives you sodium chloride in a solid state. And during this, the enthalpy changes, that is enthalpy of formation of NaCl is minus 411 kilojoules per mole. But if the same change is carried out in a stepwise manner, that is in the first step, sodium solid is converted into sodium gas. Then during this, that means it is a sublimation reaction. Solid is converted into gas. So heat of sublimation is 107.3 kilojoules. It is positive. Then in second step, chlorine molecule is converted into chlorine atom in a gaseous state. This is also the endothermic reaction, and enthalpy change is 122 kilojoules per mole. Then this sodium gas is converted into sodium ion by removing the one electron, that is enthalpy of ionization it is, and is equal to 495.8 kilojoules in third step. And in fourth step, this chlorine gaseous chlorine atom accept this electron which is given during ionization of sodium gas. Accepting electron, it forms sodium chloride ion, and during this, as here electron is accepted, energy is released, and it is called as the electron gain enthalpy, and it is equal to minus 348.6 kilojoules. Now if you add all these quantities, that is 107 plus 122 plus 495.8 minus 348.6, then you will get what? Minus 787 kilojoules per mole. That is what? The enthalpy of lattice enthalpy of sodium crystal. That is enthalpy change when 1 mole of a ionic solid is formed from its ions, that is sodium ion and chloride ion in a gaseous state. And as here the sodium chloride is formed, energy is released, and it is equal to how much? Minus 787 kilojoules per mole. Now when you add all these quantities, then you will get what? The lattice enthalpy, crystal lattice enthalpy. So crystal lattice enthalpy is the enthalpy change. Its value is positive because amount of energy is required to separate these cations and anions. When enthalpy of solution, we have studied what happens. Sodium crystal, when it is added into water, that is it gets solvated, first step is what? The separation of cation and anion takes place, and the same amount of energy is required to separate this sodium and chlorine. So plus 787 kilojoules per mole. This much amount of energy is required to break the bond between sodium ion and chloride ion in a crystal lattice, and that is called as a crystal lattice enthalpy. So like this, you can calculate crystal lattice enthalpy by adding all these equations, and that is nothing but application of the Hess law. According to Hess law, what it is, the main application of Hess law is it is used to calculate the bond enthalpies of those reactions whose enthalpy change is not carried out experimentally. So like this, you can calculate the enthalpy change for those reactions whose enthalpy change you cannot calculate directly by experimental method. So thank you.